So next, let me introduce our keynote speaker, Jurgen Schmidhuber. He's the co-director of the Swiss Institute for Artificial Intelligence, which is IDSIA, IDSIA, and professor of cognitive robotics at the Technical University of Munich, and professor of AI at the University of Lugano, Switzerland. He got his doctoral degree from Technical University of Munich in 1991. His habilitation degree in 1993. I admit I don't know what that is, but I guess it's something impressive. But, second PhD. Well, we only have one here in the U.S. And, he has helped transform IDSIA into one of the world's top 10 AI labs. It's the smallest of the top 10 AI labs. This was ranking according to Business Week magazine. And a member of the European Academy of Arts and Sciences. And he's published a couple hundred papers on pretty much every topic under the sun. And the reason I invited Jurgen to be the keynote speaker is I really felt he combined three things in his work, which is quite rare to be combined in one guy. A broad, grand vision of AGI and all its future prospects and potential grandeur. A lot of rigor in mathematical formalization and kind of formal understanding of what AGI and intelligence are about, and really solid, practical, useful work in the AGI and AI algorithm development. So being able to combine the grand vision, the mathematical theory, and practical algorithm development so well in such a long time in so many papers, I think that's quite rare. There's not many people you can say that of. So I was very happy he came and agreed to speak for us.
Thank you very much, Ben and organizers, for this invitation, which I consider a great honor. I was talking about three prisoners that were sentenced to death, one of them French, one of them German, one of them British. What is your last wish? They ask the French guy. He says, one final exquisite French meal with exquisite French wine. What is your last wish? They ask the German guy. He said, I want to give a speech! What is your last wish? They ask the British guy. He says, I want to get shot before the German starts his speech. Unfortunately for you guys, it's too late now, because already in the middle of my little speech, luckily, Ben already told you everything about what AGI and the new AI could be. So I only have to add a few aspects of the new AI that I personally consider important. This is the title of my talk. This is my name. This is to help the chairman pronounce my name. And I have two affiliations. Two affiliations. One is with the IDSIA, with the IDSIA in Lugano, and there we are currently trying to hire a bunch of postdocs and PhD students for robot learning, machine learning, universal artificial intelligence theory, and things like that. And the second affiliation is with the TU München Karlsbad lab, where we have all kinds of interesting robots. So this is actually not ours, but from the lab next door, roughly my size, and was the first humanoid with sophisticated vision such that it could walk across obstacles a couple of years ago. Today the Japanese are leading in that field. That is a robot which is the successor of the first robot that was able to tie knots. And this is the one that we are using for our students, to train the students. And why do the slides look the way they do? Well, because they're all designed according to recursive applications of the harmonic proportions. And the reason why they are designed this way is because this reflects something that will be a topic later in the talk, namely compressibility. Whenever you have a simple regular scheme like that, then there is an aspect of what you're seeing that is highly compressible. And compression has a lot to do with optimal inductive inference and optimal decision making and Occam's razor and things like that. And so in that sense, the slides reflect a little bit what I'm going to talk about. Now, there are many ways of putting labels like old AI and new AI and stuff like that on all kinds of research. One of them is this: you can say the old AI is logic programming and expert systems, then the narrow AI or the standard AI, or whatever some people might call it, the one which is now dominating most of the activity in this field, is about embedded agents that are somehow embedded in a bigger world. They are interacting with robots, for example, or internet agents, etc. And the way to deal with them is, and to make them learn something about the environment, is based on probability theory. So much of current AI is actually just a variant or extension or epsilon additions to traditional probability theory, Bayesian analysis, and etc. And you have very successful reactive learning mechanisms, sub-symbolic learning mechanisms. I think I have a pointer somewhere. Thank you. Reactive sub-symbolic learning, like for example support vector machines or feed-forward neural networks that take an input pattern and map it to some output pattern, some classification, and make assumptions such as all these patterns are statistically independent, and they are used to drive cars like this one, that is a self-driving car, an embedded agent living in the real world. And companies like Google are indeed making a lot of money with this type of AI. And one way of putting a label on the new AI would be that we are also now going to be very interested in non-reactive mappings from sequences to sequences, not just stationary input patterns to output patterns, in methods that learn entire algorithms and programs and behaviors where you have to memorize previous events in order to do the right thing at a later point in time. That's something that the support vector machines and all these really successful devices of recent machine learning cannot do. And what I think is most important in this context is that we now, for the first time, have an AGI which is mathematically sound. There is a mathematically optimal way of decision-making in unknown environments, which can be proven to be optimal in certain senses. And in that sense, we are now in the middle of seeing AGI becoming a formal science as opposed to a bunch of guys playing with robots. Now, this is one of the heroes of traditional AI or standard AI. That is Ernst Dickmanns. Ernst Dickmanns is the pioneer of autonomous driving. In the 1980s, he built machines like that, and his team, of course. There's a Mercedes van, and it has cameras on board. And back then, when computers were 1,000,000 times slower than today, he was able to drive already on empty streets in Bavaria. And in there, you had huge computers. And then as the computing power and the algorithms improved, he put it into smaller machines like the Mercedes-Benz cars like that. And then in 1995, that was 15 years ago, he already had a car that was able to go from Munich to Denmark and back on the Autobahn in traffic, tracking up to 12 other cars simultaneously using active vision to do that. Using Kalman filters and statistical approaches to deal with uncertainty in the measurements, etc. Passing other cars automatically, identifying other cars, passing them with up to 180 kilometers per hour. So that is my hero of autonomous cars. And then later we also saw other self-driving cars. But you know, the DARPA Grand Challenge, maybe some of you have heard about that. There you didn't have traffic, and the cars were actually driving by GPS, so you had navigation things on board, and to do a single curve you had to follow 4 GPS points, and in between there was just a little bit of vision necessary to not lose the road. And more interesting was then the challenge of 2007, where you had to observe traffic signs and all kinds of more complex pattern recognition problems had to be solved. And in the same year, just 15 minutes from our institute, we had the European Land Rover trials. And here we see pictures of cars in rough terrain showing off their autonomous driving capabilities there. Well, here's another example of traditional AI, standard AI of the embedded kind with learning machines, but not in the general sense that I mentioned a few slides ago. Here we see Alexander Förster. He is a postdoc in my lab at the ITSIA. And his main claim to fame is that he was the leader of the team that won the RoboCup in the Fast League in 2004. And the Fast League is probably the most interesting of these robot leagues because these guys are so fast that you don't, that a human expert with a joystick cannot win against the best teams. Cannot win against the best teams. And each of these robots here has 4 little wheels, and they have a little learning mechanism on board that makes them predict what is going to happen if I send this command to these 4 particular motors. Each of them is slightly different. So first there's a learning phase where the robots learn what's going to happen, and then you can use these predictions to plan ahead, tick, tick, tick. And in that plan, there's still the option, you can modify the action sequence that you're going to execute in the near future such that a certain goal is reached without bumping the ball away and stuff like that. But the global behavior is scheduled and pre-wired and pre-programmed. So that would be an example of traditional AI where something like a feed-forward network or a support vector machine or hidden Markov model or something like that is used to train a little part of the machine such that it's part of a bigger thing where then the whole the whole system solves some interesting task. The future will be more, at least the future of machine learning will be going towards learning programs, algorithms in machines that have an internal state that can memorize previous events in some sort of internal memory and can learn which of these many events that are coming in the input stream are important and which can be ignored, etc. And in the end, let me, in the next slides, show you a few examples of what can be done today, and then finally I will move on to these universal methods. How many people in this room know what is a recurrent neural network? Okay. How many people in this room do not know what is a recurrent neural network? And there's a quantum superposition, people who have no idea, okay. So, a recurrent neural network is a little bit like the thing that we carry around in our brains. You have all these nodes and they are nonlinear, and what they do is they sum up the activations of their connected friends where you have a program that is actually embedded in the synapses in the weights, which are real-valued numbers essentially, and they define the behavior of this recurrent system which receives a stream of inputs, and while new inputs are arriving, old inputs are still somehow circling around inside according to the rules determined by this parallel sequential program embodied as a white matrix. And these recurrent networks are as powerful as any traditional computer you can implement on such a recurrent network, any algorithm that you can implement on this computer here. But unlike with traditional computers, what you can do is in supervised learning you can train the network to become a better computer because you can evaluate the difference between what the network should do and what it really does, and you can differentiate your wish, which is that this thing should be really doing what I want to do. You can differentiate this wish with respect to the program running on the computer, on the recurrent network. So you can generate a gradient in algorithm space, in the space of possible programs, parallel sequential programs that are running on these recurrent networks. The learning algorithms that we are using today for these methods are not universal, but already pretty general and especially useful in quite a few applications, especially in the so-called long short-term memory networks, LSTM networks. Here we see a picture of Sepp Hochreiter, who was the first author of the paper back then in 1997. And the main advantage of these LSTM networks, I'm not going to go into details, is that they overcome problems associated with the previous, with the old recurrent networks, which weren't able to deal with long time lags between events in a way that was clearly superior to standard feed-forward networks. So with these LSTM networks, suddenly you could do all kinds of interesting sequence processing tasks where you had to memorize things for thousands of time steps. And today they are, back then in the 90s, they were just toy applications, but now we have all kinds of state-of-the-art applications, for example, in protein prediction and certain aspects of speech recognition, where the main competitor is usually the hidden Markov models. How many people know hidden Markov models in this room? Okay, wow. And Markov models is the main competitor usually, and handwriting recognition, connected handwriting recognition, which is much harder than isolated character recognition. For example, here we see a picture of Alex Graves, who used to be a student at the ITSIA in my lab and now is a postdoc in Munich. And suppose the problem is to translate this handwriting here into letter. So that would be a T, O, B, E, W, I, L, L, I, N, G, T, O, and so on. Now, there is no teacher who knows which, what is this scribble here, or is that here part of the N, or is it part of the I, or whatever. All the teacher knows on the training set is a sequence of labels. That would be the target label sequence that you want to output, given the real valued input that you get as you are feeding this connected handwriting here into a recurrent neural network. From here to here, that's about 600 time steps, and then actually there is not only one recurrent network that is trying to predict the next letter given the context, the left context that it saw so far, going from here to here, for example. But there's another one which goes the other way around, which goes from the future into the past, such that at each point in my connected handwriting, I get two different outputs, one from the forward network, one from the backward, from the reverse network, and you add them all up, and then you get again a gradient in this space of algorithms defined by these two network architectures, and you just improve your program again by computing the gradient of this thing here, which is the probability of the output sequence in the training set, of the output labels in the training set, given the input sequence. And then and it turns out that this works amazingly well, much better than with any other approach that is known at the moment. So for connected handwriting, this is currently state-of-the-art. And connected handwriting is much harder than isolated digit recognition. With isolated digit recognition, support vector machines and traditional machine learning methods, convolutional neural networks, they achieve performance which is identical to the one of the best humans. Now down there you see a little movie which corresponds to a sensitivity analysis of a network that has already learned the behavior or the correct translation. Here we've got 600 time steps, and whenever you see something spiking up, it tells you how important is this event here or something back here in the past or here to make the correct decision at this point where the network is making decisions. So where you see the most concentration of blue, there is the decision point, and here is where the letters are being generated. And often you see that correct decisions require information that is hundreds of time steps in the future or in the past. Or here, keyword spotting. This is a picture. Oh, this reminds me. Last time I was in America, this was a couple of years ago, and everything was slightly different back then. Some things were totally different. For example, there was a totally different president. The older ones still remember. And back then, everybody was afraid of Al-Qaeda, and one of the ideas was listen into 1 billion phone calls and check for suspect keywords. And this is what Santi did here with a large corpus, and again, the main competitors are always HMM in that field, and he was able to achieve much better performance with these double recurrent networks on keyword spotting than the other approaches. Now, of course, this does not only have military applications, but also commercial applications, such as industrial espionage. But today, of course, most people are less afraid of Al-Qaeda and they are more afraid of their investment advisors. The other day, my investment advisor called me. He said, I've got good news and bad news. The good news is the money that you invested, it is still there. The bad news is it doesn't belong to you anymore. Now suppose your investment advisor is confronted with a stock market curve that looks like that, or like that. These are 300 time steps, and it doesn't really matter, is it milliseconds as a unit interval or days? And the idea is you want to predict the future of this time series and buy low and sell high in the future. The future is this here. Now, I personally don't know any investment advisor who is able to predict the future of this time series, but recurrent networks have got something to offer for everybody, and if we feed our recurrent networks with the beginning here, with beginnings of time series like that, then those with the good eyes, they will maybe see that the little black dots, which represent the predictions of the network, they're almost always right on target. Sometimes you have little deviations there, but actually there's a regularity in this little piece of data, a few hundred time steps of data, that can be used to extrapolate to the future in the correct way. Down here, it's always, it's also the case. So another interesting application, potentially lucrative application of recurrent neural networks, or robotics. Like this thing here, which is trying to tie knots. You have actuators, and you're working in a very confined area in this artificial animal down here, where you have a narrow cavity, and then a surgeon is showing how to tie knots in this cavity. And it's hard, also for the surgeon, it takes a couple of minutes, and you do that a couple of times to show the network what is going on. And then you have the typical state disambiguation problem, because again and again you get inputs that are identical, although they represent a different part of the trajectory, of the knot tying trajectory, and different decisions have to be made, although the input is the same. So you have to memorize which kind of input did I have before in order to do the disambiguation. And again, these recurrent networks can do that, can learn that. Or more recently, you can even build recurrent networks that take the two-dimensional bias of images in form of a pre-wiring and can excellently recognize characters, outperform traditional methods on certain types of character recognition, and are especially promising for movies and object recognition in movies. But if there's no teacher, that tells the system on a training set what should be the desired output, if there's just a reinforcement learning task where you try to solve a problem like this one. This is a picture of Faustino Gomez, who got a Best Paper Award for this. Here we've got a rocket which has fins, and it's kind of heavy because the fins they weigh something. So if you remove the fins, then the rocket is lighter and can get higher, but it's harder to control the rocket then. And without fins, the rocket does something like this. It goes up, and at some point the boosters are miscontrolled and the whole thing explodes. But you can devise an evolutionary neural network algorithm, a learning algorithm, whose only feedback signal is the height of the rocket that is being achieved. And if it's better than the best so far, then you get a positive reinforcement for this network, which can be a recurrent network down here, which is controlling the boosters. There's no teacher who knows how to do that, so the only feedback is at the end of the trajectory, and the question is, does it get higher than the highest so far? Now, if you have many parameters in your network, then the problem is that traditional evolutionary algorithms do not work, because they don't really work with these long genomes. But what you can do is you can have a lot of separate evolutionary processes running on all these little neurons here, such that each of them has a population, a subpopulation, just limited to its own weight vector, which greatly limits its search space. And they all get the same feedback signal. And it turns out this works surprisingly well and outperforms all other kinds of competing algorithms. Oh, here's another application where you have a recurrent network that is steering a robot that has 3 wheels. The wheels look more or less like that in the real world. In the physical simulation, you have realistic friction, etc. You have 3 of these recurrent networks that are controlling the wheels, and there are sensors that tell the network, that tell the robot what's going on. Is there an obstacle nearby, etc. And there's a pole on top of the robot, and the goal of the robot is to balance the pole. And after maybe 3,000 iterations, it really learns, first of all, to balance the pole, but then also not to run against the wall. And the only feedback is based on trial length. So is the current trial better than the best so far? Yes, then you have a higher probability of surviving if you are part of the subpopulation of these recurrent neurons here. So that can be learned. Now, if we take the same robot and we add a second pole and stand it on and put it on top of the first pole, after 4,000 iterations, what we get is an almost perfect behavior, but now you see in a moment that this is really 2 poles standing on top of each other, because this one here crashes. But after 5,000, 6,000 iterations, it really knows how to do it. And again, no teacher telling the robot what to do. And it turns out that if you put this idea a little bit further and then you co-evolve all the synapses in the network, then this leads to, on the cerebellum-like control problems, leads to the best performance on challenging tasks. It turns out that the traditional reinforcement learning algorithms are no real competitors anymore, and the best competitors are usually always some sort of evolutionary method. In particular, CMA, covariance, matrix, adaptation, evolution strategies. That is one of the gold standards, or maybe the gold standard in that field. But cosine outperforms it, at least in this particular application. Does anybody know, has anybody ever heard about covariance matrix adaptation? Okay. Ask your neighbor, he'll explain. Well, here's another application. You have an object moving through water, and there are little actuators on top of the object. And the goal is to make them learn to move such that they create counter turbulence, such that the turbulence that is generated by the moving object is somehow killed, and there's less drag and less resistance. And if you have then a realistic simulation of what's going on, it looks like that a little bit. But then if you look at the vortices before learning, they look like that, but after learning, they become much smaller, you see that? And the drag goes down to about 40% of the original value. A couple of years ago, again, we did that and was state of the art back then. Or we are training these guys, these humanoids, to walk not only on flat terrain like that, but also on rough terrain. And here, the new type of research that is relevant here is closer to the theory of computation and algorithmic information than to the traditional statistics field. And here are some of the heroes of computation. Gödel, who started the field of theoretical computer science essentially in 1931 with his paper about the limits of computation and proofs. Turing, a few years later, reformulated these results together with Church, And this guy is interesting. Kolmogorov in 1933, he was the one who wrote down for the first time the axioms of probability theory, and was so displeased with these the basic ingredients of probability theory that 30 years later he came up with this alternative definition of complexity and of information, which is today known as the Kolmogorov complexity, the length of the shortest program that computes something. That is the Kolmogorov complexity of the something, the algorithmic information that is contained in this object. And in many ways, these notions are closer to what's going on in these recurrent networks than what we can learn from traditional statistics. Currently, we are writing the RNN book, the recurrent network book. And now, let me switch to the universal stuff, because yes, these recurrent networks, they are general in the sense that you can really run arbitrary algorithms on them, but the learning methods that we have seen so far are limited because they are greedy. For example, gradient descent is actually a greedy method. Evolution methods are greedy methods in many ways. And it turns out that there are best possible ways of learning programs for computers that are as general as these. And to introduce those, let me first start with my little IQ test. Are you still awake? So I'm going to show you a pattern, a series of numbers, and there's a pattern hidden in these numbers. And you are supposed to think about it a little bit and then tell me what is the next number. So here is the pattern. What is the fifth number?
0.
0. 0 we have here. 10. The answer is 34. Because the nth number is this. The nth number is this. But if you say 34 in an IQ test, it could happen to you that you won't get the full score. Because what the IQ tests want from you is a simple solution. They want you to say the solution is 2n as opposed to this. And the reason for that is this man down here. Occam said simple solutions are better. Simple solutions are better. If you have 10 different explanations of the data, take the simplest one. And Kolmogorov formalized that. And he said, as I already mentioned, he said, well, simplicity can be measured by the size of the shortest program that computes the thing that you want to describe. In that case, the polynomial. So 2n somehow needs a shorter program to be described than the long polynomial that we had. And Solomonov, this man over here, this is a picture I took at the ITSIA in 2001, and he's still alive and kicking. He was the one who came up with a fundamental way, an optimal way of predicting the future of time series like the ones that we just saw from the previous observation or observations. And because that's such an important concept, how many people already know how that works? Okay, so maybe 10%, and the others are going to learn it right now. It's such an important concept. Everybody, every scientist, not only every machine learning person, every scientist, I think, should know this. Suppose you want to predict the next observation, xn plus 1, after you already saw x1, x2, x3, xn, etc. The next observation will come with a certain probability mu. What's the English name of saying mu? Mu, okay, mu. So the probability is mu that xn plus 1 will happen, adopt a certain value, given all the previous observations so far. Now, you predict the next element from the previous ones, not with the true prior, which you don't know. With the true probability distribution, you don't know that one. Instead, what you say is you generate a new a priori distribution, which is this mixed prior here, which essentially is all the computable distributions taken together. Each of them gets a little index, so mu L is the Lth computable distribution of the Lth computable a distribution that assigns a value xn plus 1 given the observation x1, x2, and so on until xn. And each of them gets a little weight. And ideally, this little weight here is the Kolmogorov complexity of the program that computes that probability distribution in the exponent, in the negative exponent of 2. So you have this as a weight. This is something that is, 1/4, 1/8, one small number. And the sum of these little weights cannot be more than 1. And so by summing all of these distributions, you get a new distribution which in some sense encompasses all the other computable distributions. Now you predict with this prior, instead of the true prior, which you don't know, which is this one, which you don't know, and it turns out this is the best thing you can do in a very general sense. So there are theorems that show that this is, in a certain sense, the best thing you can do. And this guy here, he, 40 years later, he put it together and used that distribution to build an optimal universal decision maker, an optimal universal AI. This is Markus Hutter, at a time when he was still postdoc at the ITSIA, but then he became a professor in Canberra where he's still working. And this little formula, I just explained what it means. It just says, takes the universal distribution of Solomonov and extend it a little bit such that actions are taken into account. So you always have an action, and then an input comes, and you do another action, and another input comes, etc. And then you try to maximize, you try to select for the future the action that is the first action in the sequence of actions that maximizes the mixture predicted reward in the future. So you want to maximize the expected reward that you will obtain in the future, the total cumulative future reward. That is your goal in life. You want to achieve that. And what you should do is, and there's a proof that this is really the best way to do it, you should execute the action that begins the sequence of actions that will lead to a maximal mixed predicted reward, although the mixture, the universal mixture of Solomonov is very different in general from the true prior, which you don't know, from the true way the world works, which is one of the many things that are there in the mix. So that, I would say, is a new AI result. You have a very simple equation, and it is not a huge software package that describes AI, a huge AI system or something. It's just a simple equation, and there's a proof that says this is the best thing you can do. So that is one of these results that shows that AI, general AI, is on its way of becoming a formal science. Now, you may say, it's not computable, this thing here, because there are so many computable distributions, and there are, in fact, infinitely many, and so how do you deal with that? But there are ways of, relaxing a little bit, or actually making additional assumptions which are not too restrictive. For example, suppose that it's true what Konrad Zuse already predicted in the 1940s, namely that the entire universe that we are living in is computed on a cellular automaton or some other sort of computer, is a computable universe. There is no physical evidence against this possibility. If that is true, then it would be nice to know that program, and of course all the physicists, that's what they want to do. They want to find the program that computes the universe, if there is any. Now, at the moment we don't know this program, but if we make the assumption, just to get a computable way of dealing with this problem of universal AI, if we make the assumption that whoever is running universes and whoever is running this particular universe also has some sort of resource constraints and wants to find fast ways of computing universes and really likes the quickly computable universes much better than the others. If you assume that, then there is then you will quickly be led to the optimal way of computing all kinds of things, which goes back to Levin. There's an asymptotically optimal way of computing things, including universes. And from that you can derive the so-called speed prior, which essentially assigns, unlike Solomonov's prior, which assigns high probability to things that have a short description, this one assigns high probability to things that not only have a short description, but also can be quickly computed. And then if you take this one as a prior, it is restrictive enough such that you become suddenly, that you get a computable strategy of acting in the world such that your future reward is maximized. Another result, which really goes far beyond the incomputable things, is this. Another result of Markus Hutter. He came up a while ago with the asymptotically fastest algorithm for all well-defined problems. Do you already know this algorithm? How many people? Okay, so many people in this room do not know the algorithm, but it's a very nice and very simple one. So any problem that you can think of, as long as you can formalize it and write it down formally, such that you have a domain and a domain of problems and then a solution space. For example, you want to solve traveling salesman problems, and there are many traveling salesman problems. Now you get a traveling salesman problem as an input, and there's a function f that computes a solution to the traveling salesman problem in the domain y. Then what you do, this super algorithm here, it searches systematically for proofs until it finds a program Q that provably computes the function that you want to solve for all elements in the domain, for all traveling salesman problems in the domain, within a certain time bound, which depends on Q and on the instance, which is Z. And then there's a clever way of allocating runtime such that you spend most time on the program with the best currently proven time bound. You look at this algorithm, and then you can prove this. As fast, this algorithm here, which does not know the solution, doesn't know anything about traveling salesman problems, will compute your traveling salesman problem solution as quickly as the fastest traveling salesman solver, which you don't know it. Say for a small constant, 1.001 can be arbitrarily close to 1, so you almost don't lose anything here. Plus some constant which depends on f, but not on the problem, which depends on the problem class, but not on the problem instance. So, that's the end of computer science. Except for the one little drawback that the proof search here corresponds to this constant down here, and it can take a long time. Although it's constant, the constant may be so large that it doesn't really fit in this universe. Order n to the 3 plus 10 to the 10,000 is still order n to the third, and in the O notation of theoretical computer science, it falls out of the picture. But in the real world, it doesn't. So this shows that asymptotic optimality can be misleading. This guy over here, maybe he's asymptotically optimal, you know? But it won't buy him anything. What can be done? How much more time do I have?
45 minutes.
Oh, right. What can be done? Well, one thing that can be done to overcome the problems with the Gödel machine, to overcome the problems with the constants is the Gödel machine. And to construct a Gödel machine, we have to go even further back in time, not only to the 60s when Solomonov and Kolmogorov did their work, but to the 30s when this man here, Kurt Gödel, founded essentially theoretical computer science by showing which are the limits of computation and of math in general. What he did, he created a self-referential formula that speaks about itself, and it claims to be unprovable by an algorithmic theorem prover that systematically generates theorems. So the formula says, I am not provable by an algorithmic theorem prover. Either this formula is true, but it's not provable then, or math itself has an algorithmic flaw in it.
Actually, we should probably leave some time for questions. Maybe 35 minutes.
All right. Easily. Now the Gödel machine is just, how many people already know what a Gödel machine is? Then I skip all of this. Oh, I can skip. Do you want me to skip it?
No, it's interesting.
No. So the Gödel machine is just a computer which has a software on it, an agent controlling program that also is self-referential, so we steal that trick of Gödel. And it speaks about itself, and it's ready to rewrite itself in arbitrary manner as soon as it has found, through an inbuilt theorem prover proof, that the rewrite is useful according to a utility function that is given by the user, which can be any utility function, not only asymptotic optimality can be embodied by this utility function, but anything. So again, you plug in the initial software, which I call P, you plug in any utility function as an axiom stored in this initial program. The program interacts with the world, and while it does that, while it steers a robot like this one here, it also makes pairs of Q and proof, where Q is a little program and proof is a proof that the Q does something, until it finds a proof of the rewrite of the initial software of P through this program Q that it just found here implies higher utility than leaving the initial software as it is. Now with that approach, the Gödel machine will optimally speed up itself, including the proof searcher. So it's not like with the asymptotically optimal general problem solver, which has a hardwired proof searcher that cannot be changed, that cannot be improved as something. Instead, the proof searcher itself can be rewritten, replaced by something else, possibly. And any of these self-rewrites is necessarily optimal, globally optimal. There cannot be any local maxima, since the proof itself, if you think about it, and that's the whole point of the self-referential business, necessarily must have demonstrated the uselessness of continuing the proof search for something else, for some even better rewrite. So we are almost there. But one important question, I think, that is something that hopefully will be answered in the coming years. Before the first self-rewrite of such a Gödel machine, let's focus on this question. If there are only C instructions per second, say 10 trillion, why 10 trillion? Because your brain maybe does something like 10 trillion instructions per second. What is the best way of using these 10 trillion instructions per second to get as close as possible to the theoretical limits identified in the previous work? Now, I don't know how that is possible, but it seems to me that one thing that is not entering the hasn't entered the discussion so far is that we should further bias our system towards regularities, such that it's still very general, but it should be biased towards regularities in the following way. It should be the learning agent should be able to design its own experiments, its own tasks, to figure out which are the interesting parts of the world, where interestingness essentially corresponds to the things that are learnable, but not yet known, learnable regularities in the world, which its own limited learning machine can learn quickly. So it should be able to have this additional freedom of generating its own tasks to figure out which parts of the world contain some regularity that I don't know yet, and this is something that I'm going to learn. And the hope, of course, the only reason why this might make sense is that the external rewards, like filling the battery by plugging into the wall or something like that, also have a lot in common with all these regularities that you find in the world. It's not, if it is true that I cannot get a lot of reward by doing something random, like standing in a certain position, starting to pray a certain random prayer, and then the reward is thrusted upon me. If that is not the case, if all the reward sources in the world really have a lot to do with the regularities, then this is one way of greatly reducing the search space by biasing the system towards the regular parts of the world. And this is actually a different type of talk, a different talk that I like to give, which where a very simple principle helps me to explain essential aspects of novelty and interestingness, and also beauty and discovery and science and curiosity and art and creativity. And it's very simple. I just want to spend one slide on that, such that you know what I'm talking about. First of all, the intelligent agent that wants to use its limited instructions, its 10 trillion instructions per second, for example, in a wise way, what should it do? Well, if it can do this, then it should certainly store its entire life, because the entire life is, or the data that you get from the environment, that's the only thing that it will ever really know about the environment. That is the anchor of everything that can be inferred. Now, it turns out that a human brain apparently is able, I did a rough calculation, of storing 100 years of lifetime at the rate of about 10 to the 5 bits per second, so it would be like a low resolution MPEG movie. And technical systems will soon exceed that value. So if that is possible, that is just a hardware problem. If that is possible, then don't throw the data away. So that's a very simple thing that you should do. Now, you shouldn't just store the data, you should try to explain it by compressing it. If there's a regularity, repetitive regularity in the data, compress it. And here my little definition of beauty of some data point x at a given time t in the system lifetime, it's essentially the number of bits that you need to code the data x at time t. For example, suppose you run around with a prototype face that you use to encode new faces. A new face comes along which looks very much like the prototype face that you have in mind. Then you can encode the new face by just encoding a few deviations from the prototype face without wasting a lot of storage space. Now, the other thing is, if a face is very regular, then but within the limits of what is natural, then you again need just a few bits to store this new face, and so in that sense you can argue it's a beautiful face. But this is not the point. What you have to do all the time is not only compress it, but continually try to improve the compressor. For example, if your compressor is a recurrent neural network like that, which tries to predict the next thing from the previous things, the better you can predict, the better you can compress, because everything you can predict, you don't need to store separately. So if that is a recurrent neural network, then it will learn to become a better processor and predictor over time. It has, during sleep, all this data available where it can work and try to compress better. And then, what is then the interestingness of some data? Well, it's the first derivative of the beauty. It's the first derivative of the number of bits that you need to encode the data. As you need less bits to encode the data, as your explanation of the data improves, the interestingness of the data is proportional to the change, to the derivative of the number of bits that you need. And this is your internal reward. That is your happiness. That is your wow effect that you get as you are explaining something that seemed unexplainable before, but suddenly you see there's a regularity, and in that moment you get the reward. And that is what you need as an additional reward for the controller, for the action selector, the curiosity-based action selector that tries to find data in the world that is compressible in a new way that wasn't already known. Okay, that's it. So a discovery is just a large improvement in compression performance. For example, if you are a physicist and you watch apples falling down and suddenly you see, hey, they're always falling in the same way. There's a law behind that. Then with that simple law, you can greatly compress your inputs. But if you didn't know that law before, then suddenly you have a huge compression improvement. Or in the arts, in the arts, when you have a guy who, for example, is drawing a picture of Obama, let's say, but just 5 lines are necessary, and everybody recognizes this is Obama, then it means that he has extracted the essence in a very compact way, and the first time you see that, you think, oh, that's interesting, so that's why you look there. There's a new regularity that in that sense you didn't know before. And in that sense, the scientists and the artists are both doing the same thing. They try to create or find data that is compressible in a new way that wasn't known before. One take-home message, if there's any, one important ingredient of the new artificial general intelligence, in my point of view, is that for the first time you don't have this heuristics-dominated approach anymore, but now you try to create a formal science which is based on optimality theorems, and they are based on a combination of probability theory and theoretical computer science. And heuristics, they come and go, but theorems are for eternity. So that is maybe the main reason why we are why formal sciences are preferable, and it's a long time. And can we also say something about the near future? Well, this would be the third part of my little presentation, which Ben asked me to provide, and this would be the fun part, but we can skip that.
You can take a few minutes.
A few minutes. So this is a picture of Werner Winch in the 80s when I was a young man. Seems unbelievable today, but there I read these novels of him about the technological singularity. So the idea back then of Werner Winch was accelerating progress gets faster and faster, and at some point becomes incomprehensible, and you have this thing that he called the technological singularity. And first he published that in science fiction novels. And I read so many science fiction novels back then, and these were one of the, and most of them were really bad, but this was really interesting stuff, I thought. And then later I read in a book by Ray Kurzweil that actually is the first guy who came up with this idea of a converging history, singularity, probably, perhaps, I don't know, was Stanislav Ulam. And this guy here, Werner Winch, though, is probably really the first one who elaborated on that concept in many, many ways, not only in science fiction novels, but also in scientific publications. Now, I asked myself, is it really true? Is there such a pattern in history that fits that idea of a singularity, a historic singularity? And yes, there is one. And it's amazing how simple it is. It turns out if you take as a basic interval a human lifetime, which takes 80 years, then the nth main chapter of history in the history books, you just open a history book, is 2 to the n human lifetimes before omega, the singularity, which is for some reason in 2014. And let me show that to you. So omega is 2040. Many people are coming up with a number like that, 2040. So I take that as well. I say one lifetime is 80 years, and it's true that always there have been lifetimes like that. And the average lifetime of previous millennia was shorter, mostly because of the high infant mortality. So 80 years always was a good lifetime. And my error bars are not, in most cases, they are really much smaller than 10%. Now, 2 to the 9 lifetimes ago, 40,000 years ago, Homo sapiens comes into existence and colonizes the world. And we take half of that, and we hit exactly, as far as we know, the invention of long-distance weapons like bow and arrow and the hunting revolution, and we take half of that. And we hit exactly the beginnings of civilization, the invention of agriculture, the first permanent settlements, and the first walls, etc. And we take half of that. And it's exactly the first high civilizations in Sumeria and Egypt, and the most important invention of recorded history, the one that made recorded history possible, namely writing. 5,000 years ago, it's not quite clear, in Sumeria or in Egypt, and we take half of that. And it's exactly the peak of the ancient world under the Greeks. Back then there was this huge empire, the Persian Empire, which in many ways was much more remarkable than the Roman Empire, but it's not as much covered in Western history books. But it had probably almost half of humanity in there, and probably clearly more than half of the world economy. And it existed 2,500 years ago, and at the fringes of the empire, exciting things happened, especially in Greece. In Greece, during that time, all the basic Western values were created. Democracy was invented, philosophy as we know it. The first formal proofs appeared. Perfect, anatomically perfect sculptures were made for the first time. Engines were created. The steam engine is a Greek invention, but was not commercialized back then. Harmonic music was invented. The basis of all Western music, organized sports, the Olympics and things like that. And at the same time, the Old Testament was written, the basis of the 3 Abrahamic religions. And at the same time, in the other part of the world, in India, the Buddhism was created. And Greece was not the only technologically advanced part of the world. In China, the first calculation tools emerged. India invented the zero. So that was an amazing time back then, and we take half of that. And it's exactly the golden age of the Islamic world, the Islamic golden age, and at the same time, the most important invention of the past 2,000 years took place, namely the invention of bookprint in China, omega minus 1,300 years. And we take half of that. And it's exactly the beginning of the new age. Well, at the end of this, almost right now, at this point here, the Mongolian Empire was the largest empire ever and contained most of the known landmass, and the 2 major civilizations of that time were within its borders. And the Chinese invented guns and gunpowder and rockets, and did the first explorations. So Zheng He, he explored from China, the east coast of Africa and Australia, and slightly later, 50 years later maybe, the Europeans went the other way around and discovered the rest of the world, or they said they discovered the rest of the world. Yeah, like this picture here. This is of 1420, that is the ship that Zheng He used to explore large parts of the world, or one of the ships he used. And that is the Santa Maria 50 years later that Columbus used to rediscover America. That is, yeah, I call it Zheng He, but I don't know what is the real pronunciation. Zhong He, I'm sorry. So it was Zhong He. Zhong He.
He's the Columbus of China.
Yeah. And then the Western bookprint, which some people call the most important invention of the past 1,000 years, and the scientific revolution starts, and we take half of that. And it's exactly the age of enlightenment, and the first steam engine, the first commercial steam engine. Unlike the old Greek steam engines, the new common engine was really used, and Leibniz invented the binary arithmetics and built computers like this one, and Newton revolutionized physics, and this is one of his telescopes, and the fundamental theorem of calculus was published by Leibniz, and Newton also said he also had that, had found that. And we take half of that. Now we are 2 lifetimes before Omega, and it's exactly what many people call the second industrial revolution, when Otto invented the gasoline engine, and all these combustion engines, the diesel engine, etc. were created, and Daimler and Benz came up with a car. There's a replica of the first car. But this reminds me of something. You know that Obama is extremely popular in Germany. Did you know that? When he went to Germany, there were 200,000 people who cheered him. But the other day he said something shocking to many Germans, because he said the car was invented in America. He didn't say by whom, maybe by Abraham Lincoln. But now many Germans are worried that next time he will say Abraham Lincoln also invented lederhosen and sauerkraut. But then also maybe the most important invention of that time was the germ theory of disease, which saved hundreds of millions of lives and founded modern medicine. Cheap electricity became available, modern chemistry. So, and many of the big companies that are still existing today, they were founded right there. And the highest building ever was built, the Eiffel Tower was right at that time, and we take half of that. And you see, I'm always missing the awful parts of world history. I'm always missing things like the Second World War. This is right in the 60s. Omega minus one lifetime. And Sputnik starts the space age, and Apollo lands on the moon, and DNA is discovered, or gets at least a Nobel Prize for the discovery. And modern pop culture emerges, and the computer was invented long before that, but for the first time it became a commercially important thing. Hydrogen bombs give a new quality to the concept of war. And again, whenever people think things are going forward, they build the highest building ever. So back then that was the World Trade Center. And the population explosion of the 20th century, probably the most outstanding feature of the 20th century, was at its peak. It was triggered in 1908 by Fritz Haber, who came up with artificial fertilizer, and then within 1 century the population went up from 1.6 billion to 6 billion in the end. But the highest derivative, that was right there in the 60s, which in many ways defined the world as we know it today, and we take half of that. And this is now, of course. And again, people are buying the highest building ever. This is, I think, twice as high as the World Trade Center. They are building that in Dubai. And the world is transformed again by networks. So the World Wide Web was created at the CERN. Here we see a picture of the CERN, where Tim Berners-Lee created the WWW, and the cell phones, of course, and the GPCs. They transformed industry and private lives. And of course, the mathematical theory of optimal universal AI emerges right at this time. And so how is it going to continue? Well, many claim that in 2020, 1/4 lifetime before Omega, PCs will match the raw computational power of a human brain. And then 10 years before Omega, who knows what's going to happen? And 5 years and 2 years, and then, you know, obviously it's converging. History is converging. You see, here's another one that shows that history is converging. Now, it's not based on human lifetimes anymore, but on the main breakthroughs in computer science. 1623, Schickard builds the first computer. 2 centuries later, Babbage comes up with program-controlled computers. So Schickard's computer you couldn't program, you could just do certain simple arithmetic operations. It didn't work though, because maybe well, for several reasons. And then 1 century later, the first really working computer was built by Zuse in 1941. Right in a decade, in the 30s, everything changed. Justus Lilienfeld patented the first transistor. Gödel founded theoretical computer science, and together with Turing, who came up with the Turing machine. And by the end of the 30s, the field, as we know it today, was more or less established. And then half century later, 1990, the WWW was created, and within a few years changed the world again. And of course, you know something about statistics and machine learning. You know, if you've got 3 data points, then you can extrapolate without hesitation. 2 centuries, 1 century, 1/2 century. And obviously it's going to converge again exactly in 2014. Just for fun, let's redefine Omega is not 2040 anymore, but 1540. 1540. Now, 96 years before Omega, which is now 1540, the most important thing in the time-life list of the top events of the previous millennium happened, namely the invention of, or the reinvention of bookprint by Gutenberg, 1444. 48 years later, the second most important event in the time-life list of the most important events of the past millennium happened. Columbus discovers America, rediscovers America.
Debatable. Maybe it was John Hook.
How do Europeans feel about that?
Yeah. Well, and so you're totally right. So maybe a Chinese has a very different opinion about that. And of course, Columbus did not become famous because he was the first to discover America, but because he was the last to discover America. And then, 24 years later, the third most important event in the time life list of most important events of the last 1,000 years happened, namely Luther started the Reformation. Now our Chinese friends will maybe not be convinced that this was such an important thing. But do you see the pattern? 96, 48, 24? It's converging right there in 1540. And that's one of the reasons, I think, why we never had a shortage of prophets claiming that the end is near. You look at the data point, you look at the logarithmic plot, there is always some way of fitting a straight line through all these data points, especially if you ignore the data points. And so you should take all of these predictions with a grain of salt. And maybe actually there's a reason why it looks to every subject as if history is accelerating dramatically. Look at yourself. Most of your memory space is allocated to the most recent events. You still know what you did yesterday, or do you know what you did 1 year ago at exactly this point in time? So the further you go back in time, the smaller the fraction of your memory space probably that you allocate to this time. And maybe the same is true for history books. Most history books today are written about events that happened a few decades ago. And the bulk of all the history books is really concentrated on recent events and not on very distant events. So maybe there's just like an inverse speed prior where you are allocating memory in proportion, well, exponentially in proportion to the size of the previous time intervals that are, and to the distance of these previous time intervals. As you go back, you allocate less and less memory to these events. But even that, if that is so, it's still clear that we are living in exciting times, and I think it's a privilege to be part of that. And let me finish by saying one more thing. Thank you very much for your attention.